This is the continuation of the review of exam 2. In class I went all the way to question 28 depending on the section. So let's continue with question number 10. Alright, and in this case we have this isotope technetium-99, which we don't really care about this. We can just name it A. Is the reactant that is disappearing in this case. We have a half-life time equal to 6 hours. Alright, and well, we want to know what is the amount of time, alright, to decay to 25% of the initial value. In this case, because you're being given the half-life time and you have units of time there, you can really tell whether the reaction is first, second, or zero order just by looking at the half-life time, because they will always, if it's a time, always have units of time. Okay, so we have to tell you, okay, this is a first order reaction, and that's important to know because the half-life time is equal to logarithm of 2 divided by k, which is going to come handy as we move forward. All right, now in this particular problem, because of the numbers that you have here, you can use a different approach. All right, remember, a half-life time. What is a half-life time? A half-life time is the time that it takes to go from 100% to 50% of the concentration. All right, so in this case it takes 6 hours to go from 100% to 50%. All right, but guess what? If you go from 50 to 25%, well, 25% is half of 50, so that is another half-life time. If the half-life time is 6 hours and then it takes 2 half-life times to get to 25%, then time is equal to 12 hours. Alright, you could have solved this problem in that way, but if not, you can use the sort of long way, but a valid way to solve this problem, because all you have to do is calculate k, and in this case k is equal to the logarithm of 2 divided by the half-life time. Alright, and this is equal to 0.115. Alright, let's use another one there. Okay, and because the half-life time is in hours, then this is hours to the minus 1. Okay, if you're going to 25% of the initial value, that means that the concentration of A over time divided by the concentration, the initial concentration of A is equal to 0.25. Therefore, the logarithm of 0.25 is equal to minus kt. Okay, remember, we are using the abbreviated version of the first order integrated rate law that tells you that the logarithm of the ratio is equal to minus kt. Okay, it's just something that you use depending on what you have. Therefore, time here will be equal to minus the logarithm of 0.25. The minus comes because of this minus there, divided by k, and this is minus logarithm of 25 divided by 0.155. Okay, so here the logarithm of 0.25 divided by that, well, no surprise, is equal to 12. Alright, so does the previous method works every time? No, it doesn't work every time. It's just because the numbers were such that you could use that. But if not, if you have something different from 25%, then you have to use the long way. You have to calculate k, and then you use the integrated rate law for first order. Okay, here we have to determine the value of Kc for the following reaction. Alright, things to note in the reaction: you have a solid and a solid, so when it comes to K, well, you are not considering those. Alright, so Kc here will be simply the concentration of O2 to the fifth. Alright, And since the concentration of oxygen is 3 molar, then this is equal to 3 raised to the power of 5. And this will be equal to 243. Okay, 3 significant figures, 243. What do you do with 2 moles of P4, 1 mole of P4O10? You don't use them. It doesn't matter. They are solids. They will not affect the value of K. Okay, this equation or this problem is similar to the Clausius-Clapeyron equation that you had in exam number 1. Okay, except that for this particular case it's the Arrhenius equation, and the Arrhenius equation looks like the graphical form, that is the logarithm of K equal minus EA over R times 1 over T plus logarithm of A. Alright, therefore the slope in this reaction, in this equation, is equal to minus EA over R. Okay, what is the slope here? The slope is minus 104 10 to the 4th. Okay, here these negative signs cancel each other, and your activation energy will be equal to 104 10 to the 4th times 8314. And notice that we have everything in kilojoules, so we need this constant in kilojoules. So this is 8314 10 to the negative 3. Okay, and then 104 negative, sorry, 104 10 to the 4th times 8314 10 to the negative 3. This is equal to 86.5 kilojoules per mole. Okay, a catalyst increases the rate of the reaction. All right, do you want a reaction will go faster because you are slowing down movement of molecules? No, that's not quite why it does it. Okay, by providing an alternate pathway with a lower activation energy. Lower activation energy, yes, that's what we want. Okay, by lowering the activation energy of the reverse reaction, well, actually, in a catalyst will lower the activation energy for both. Okay, so but if you're looking at the reaction in the forward direction, well, is the reduction in the activation energy for the forward reaction, the one that speeds up the reaction. But at the same time, if it does a reversible process, well, the forward direction is going to go faster, but so will the reverse reaction. So anyway, the rate of a reaction will not increase just because the activation energy of the reverse reaction is dropping. Okay, it's the forward reaction that you are actually looking at. Okay, by changing the value of the frequency factor, well, the catalyst doesn't really have much to do with the frequency factor, and the frequency factor probably has not so much of a big effect there. Okay, so we are looking more at the activation energy. Remember, the activation energy is a requirement. The lower the requirement, the faster the reaction will go. So here we have to calculate Kp for the reaction that we have here, and if you remember correctly, Kp will be equal to Kc times RT raised to the power of delta N. So we have to determine what delta N here is. All right, and in delta N, here in the reactant side we have 2 moles of gas, and in the product side we have 2 moles of gas in carbon monoxide and 1 mole of gas of oxygen. Therefore, delta N is equal to 3 minus 2 equal 1. Okay, so Kp is equal Kc times RT. Okay, so Kp will be equal to Kc 1.110 to the negative 13 times R, which is 0.08206 times the temperature which is 1200. All right, so Kp will be equal to, in this case, 1.1 negative 13 times 0.08206 times 1200, and here we get 1.1 10 to the negative 11. Okay, so with this information, well, number one, we have to determine whether the reaction is at equilibrium, and if it's not at equilibrium, then in what direction the reaction will shift. Okay, we have concentrations, then we have to find Q, and in this case, since we are having concentration, we are calculating QC, and that will be equal to the concentration of NH3 squared divided by the concentration of nitrogen times concentration of hydrogen cubed. All right, so this will be equal to ammonia 0.0622 to the second, nitrogen 0.0725, and hydrogen 0.335 cubed. All right, so this is 0.0622 squared divided by 0.0725 times 0.335 cubed. Okay, and here I get 0.002. Okay, so this is Q, and Q, let's use something that I saw around. If we compare Q and K, and in this case Q is smaller, all right, and think of that as an arrow. Okay, in what direction is the arrow pointing? So the arrow is pointing to the right, so the reaction is going to the right. Okay, so the reaction will shift right. Okay, and this is not my original thought, so thanks, Ayla. Which statement is true regarding the relationship between an equilibrium constant and the free energy change for a reaction? Okay, so we have equilibrium constant and we have free energy for a reaction. Okay, so at equilibrium, delta G is equal to 0, right? Not delta G standard. Actually, delta G, the normal delta G is 0. The delta G, remember, delta G is different from delta G standard. Okay, so but the thing is, depending on the value of K, you can establish a relationship with delta G, correct? So if K is large, then the reaction as written is favored in the forward direction, and that means if the reaction is favored in the forward direction, then delta G is less than 0. And if K is small, really small, then the reaction is favoring the reactants. In other terms, you can say that the reaction is non-spontaneous in the forward direction, and delta G is greater than 0. So if we look at our options here, okay, so we have that K larger than 1 have a delta G equal to 1. Well, that's a delta G positive, right? So if delta G is equal to 1, but that doesn't add up with a large value of K. So a more positive value of K will give you a delta G that is negative because the products are favored. So this doesn't match. Okay, If K is less than 1, then delta G is negative. Well, less than 1 is favoring the reactant, so the reaction is not proceeding in the forward direction very much. So it's not really spontaneous. So that's what you would expect if you have a delta G that is negative, but that's not what you see here. So a delta G negative necessarily has to go with a K that is larger. All right, so this statement is not correct. Now, K less than 1, K really small, matches the fact that delta G is going to be positive. All right, so if delta G is positive, then the reaction is non-spontaneous in the forward direction, meaning you are not going to produce very much. You stay as the reactants, and then the reactants are favored and K is small. All right, and basically there is not such a thing as K equal to 0. Okay, not absolute 0 at the very least. Very, very small, yes, but absolute 0, no. For the reaction Cl2 going to 3 fluorine, Cl2 plus 3 fluorine going to 2 ClF3, which two statements are true. All right, so this has to do with the reaction rate. And for this particular reaction, we will have that the negative change in concentration of Cl2 over time has to be equal to minus 1/3 delta fluorine over time, and this has to be equal to plus 1/2 delta Cl3 over delta T. All right, now we can look at what we have here, right? So we are looking for two statements that are true. So we look at the first one, and in the first one we have that just the negative change in concentration of Cl2 over time is going to be equal to positive. It's not there, but if there is no negative sign, you assume that that's positive. ClF3 divided by 2 delta T. All right, so this is pretty much what you have here. All right, so those two are equivalent. So this is a correct statement. That's matching correctly what's going on here. The overall reaction rate is minus delta F2 over 3T, over 3 delta T. All right, in any of these terms, okay, this, or that one can be used to express the overall reaction rate. Those three terms are equivalent when it comes to express the overall reaction rate. So now we have negative delta F2 over 3 delta T. And that's exactly what we have here. All right, 3 delta T. And the negative sign there. Okay, so that one is correct. All right, now which ones are not correct? Why is this not correct? Because you have a 3 delta T with chlorine, which that 3 is incorrect, so that is not possible. And here the overall reaction rate equal to 2 times delta ClF3 over delta T. Well, it's divided by 2 delta T, not multiplied by 2. All right, so this 2 doesn't go there, and you need a 2 down there. Okay, so that's why those two are not valid. What is the osmotic pressure of 0.0450 molar magnesium sulfate solution at 27 degrees? All right, you're assuming a DL by half. So what is the osmotic pressure? Osmotic pressure is equal to MRTI. Okay, do we have the molarity? Yes, it's here. Do we have R? Well, this is pressure, so R is equal to 0.08206. Do we have the temperature? C? Yes, it's 27 degrees, which is 300. Not Celsius, 300 Kelvin. All right, ideal band half, what does that mean? Well, if it was a non-electrolyte, that would be 1, but this is magnesium sulfate. And magnesium sulfate, when you dissolve in water, goes to magnesium 2 plus and sulfate. So how many ions are we producing here? We are producing 2, so I is equal to 2. All right. So the osmotic pressure here will be equal to the concentration 0.0450 times R 0.08206 times temperature, which is 300, times 2. All right, and this is 0.0450 times 0.08206 times 300 times 2. And this is equal to 2.2160, which is 222. All right. Now in this question we have a beaker that contains 2 sugar solutions. They are at different concentrations, and there is a semi-permeable membrane shown below. Which figure shows the net flow of molecules and the resulting solution levels after osmosis occurs? Okay, so first thing, a semi-permeable membrane allows solvent to pass. Okay, and solvent only. Okay, so the water molecule are all the blue ones. Okay, so you are looking for your choice that is showing a flow of water molecules, a flow of blue spheres. Okay, so this one is incorrect because it's moving the solute. Okay, and this one is also incorrect because it's moving the solute. The one that is passing through the membrane is the blue ones. Okay, and in what direction is water flowing? Okay, the water flows to higher concentration. Okay, so the water will flow to whatever side has the larger concentration, and in this case is the right side. Okay, so the water here, this is showing the correct movement of water. The one with the higher concentration will have a higher level because it will contain more water. Okay, so this is the one that is the correct answer. A reaction mixture initially contains 2.4 molar CoCl2. What is the equilibrium concentration of CO if Kc is that value? All right, so we have CO, Cl2, we have CO, and we have Cl2. All right, so we have to do an ice table here. So initially we have 2.4 molar of this, 0 and 0. The stoichiometry is 1 to 1, so we have minus x here, we have plus x and plus x. Okay, so at the equilibrium it's going to be 2.4 minus x, x and x, so that we end up with Kc being equal to x squared divided by 2.4 minus x. Now we compare this value, 2.4 versus 8.3 10 to the negative 4. So you have more than 3 orders of magnitude difference there, the concentration being higher than the Kc. So we can perfectly assume that x is small, and then we have Kc equal x squared divided by 2.4. Okay, from here x will be equal to the square root of 2.4 times 833 10 to the negative 4, and that will be equal to square root 2.4 times 833 negative 4. This is 0.0447. All right, so now x here, x will be equal to the concentration of carbon monoxide, also equal to the concentration of chlorine, and it will be this number right here. If we round it, it would be 4.5 10 to the negative 2, which is the value that you have there. All right, provide the missing substance in this chemical equation. All right. So we have water, we have pH 4 plus, and then we have OH minus. Okay. I'm assuming that the equation is balanced. You have a plus 1 here and you have a minus 1 here, so you end up with a charge of 0 here. So the one thing in the other side should be neutral. All right. We can assume, this doesn't resemble like anything that has to do with water, so water most likely went to OH minus. And if water went to OH minus, that means that the water transferred one proton to whatever it was. Okay, so that proton is right here. So all we have to do is remove that proton. So pH 4 plus, we remove a proton, and then we end up with pH 3. Okay, now pH 3 to pH 4. Who has the extra proton? Is the pH 4, right? So this is your acid and this is your base. So pH 4 is the conjugate acid. Okay. The proposed mechanism for the formation of carbon tetrachloride can be written as follows. We have 3 steps. The first one is the slow step. All right. So what is the rate law for the first step? Well, the rate law for the first step is simply K concentration of Cl2. Is there anything to do here? Well, I don't think so. I think that's all we need for that, because the rate law for the first step, for the slow step, is the one that dictates what the overall reaction rate law is, right? So Cl2 is a perfectly valid substance. It's one of the reactants in this reaction. You can go ahead and write what the overall reaction is if you feel like you need to do that, but this is just okay. Okay, so the chlorine, the Cl2, only appears once and appears on the reactant side, so it's a reactant. Okay, and that's all we need in this one. Given the following reaction in kinetic data, what is the rate law for the reaction? Okay, so we'll look at stuff that change the concentration of one of the reactants and not the other. You keep the other constant to make things easier. Okay, so the rate here will be in the form of K, concentration of NO, N, concentration of H2, M. All right, so we'll first look at the first trial and the second trial. Nitrogen oxide is being kept constant here. Okay, so pretty much what we are doing, so if we call this 1, 1, 2, and 3, rate 2 over rate 1, I tend to use the whichever is higher in the rate, is equal to 5.7 divided by 1.9, and this is going to be equal to let's do it this way. We have K, and now is 0.04 N, and hydrogen is 0.120 M, and then here we have K, 0.04 again, and here we have 0.04 M. So in this situation, K cancel and these two cancel because they are the same. And 5.7 divided by 1.9 is equal to 3. And this is equal to 0.120 divided by 0.04 is also equal to 3. Okay? So in this case, well, this is 3 raised to the power of 1. From here, nothing else to do but to say that M is equal to 1. Alright, so in hydrogen, the reaction is first order. Okay, and with that, we can discard this one because it's telling you that it's second order in hydrogen, and we can discard that one because it's telling you that it's zero order in hydrogen, which is not the case. Okay, and then we move into the next one. All right, so now we will be looking at trials 1 and 3. Okay, so rate 3 divided by rate 1 is equal to 7.6 divided by 1.9, and this will be equal, well, hydrogen and the constant will be, you will discard those, so we just focus on nitrogen oxide, and it's gonna be 0.80 raised to the power of n divided by 0.04 raised to the power of n, and 7.6 divided by 1.9, this is equal to 4, and 0.08 divided by 0.04 is equal to 2 raised to the power of n. Okay, so from here it's easy to identify that n equals 2 because 2 raised to the power of 2 is equal to 4. So the reaction is second order in nitrogen monoxide. Okay, so this is the correct rate law for this reaction. A certain reaction has an enthalpy of minus 55 kilojoules and an activation energy of 121. Okay, using the diagram below, match the levels with the correct value. So, can't remember what the choices were here. Okay, but if you have a delta H equal to minus 55, then the minus 55 goes here. Okay, so here 3 is the activation energy for the forward reaction, which is supposed to be 121. Now let me erase this negative sign because that difference is 55. This number here is 121. Okay, and I'm not sure what 2 is representing here. Because so this is the activation energy, this is delta H. Can't remember if it was the numbers of the names, and here 2 will be the transition states. Should check what the options were there. All right. So on this one, remember, these are, as we move forward, these have better performance. So in the gas phase reaction, we are telling you that this is at equilibrium under this condition. So all of these are all equilibrium concentrations. So if you are calculating Kc, then that would be equal to concentration of CH4 times concentration of water divided by concentration of CH2O times concentration of hydrogen squared. Okay, this will be equal CH4, that's 0.025, water is 0.035, CH2O is 2.1, and hydrogen is 0.45 squared. Alright, 0.025 times 0.035 divided by 2.1 divided by 0.45 squared. So this is 205, 206, 10 to the negative 3, which with two significant digits, that would be 2.1 a minus 3 over 0.0021. Yeah, okay, if we have these constants here, we have these two reactions, and then with those two reactions you are to obtain the reaction of interest, then what do we have to do here? Well, to begin with, you have, let's search for carbon, which is there, okay, and then we have CO2, which is here, okay, and then we want chlorine as a reactant, okay, but you have 2 moles of that, and chlorine is here, but you only have 2, sorry, you only have 1, so you have to multiply that by 2, okay. So if you don't do anything to the first one, then you end up with Kp1. If you are multiplying the second reaction by 2, then what you are doing is raising Kp2 to the power of 2. And if you are adding the two reactions, then you are multiplying the constants. Okay? Therefore, the correct answer here would be B. What is the ideal Van Hoff for CaCl2? CaCl2, when dissociated in water, gives you calcium 2 plus 2 chlorides. So you have 1 here, you have 2 there, so you have an I equal to 3. 3 ions is what you obtain out of the dissociation of calcium chloride. Not 2, 3. Okay, the oxidation of SO2 proceeds according to the following mechanism. In this mechanism, NO2, where is NO2? Well, NO2 is here, and it's also here. Okay, it appears it's being used first and then produced or regenerated. So NO2 here is a catalyst. SO3 is here and is nowhere else. It only appears in the product side, therefore SO3 is a product. And NO is here and then here, so is first produced then consumed, so NO is a intermediate. All right. Which statement is true? Bronsted-Lowry base is defined as an electron acceptor. No. An electron acceptor is a Lewis acid. A Bronsted-Lowry acid is defined as a hydroxide acceptor. Okay. Well, a hydroxide acceptor, that sounds more like Arrhenius acid. A Bronsted-Lowry acid is defined as a proton donor, and yes, that's what we're looking for. And a Bronsted-Lowry base is defined as a hydroxide donor. The hydroxide donor, is an Arrhenius base. In this reaction, we have the 2 steps. The overall rate is KNO2 squared. Okay, which statement is true? Well, if it's KNO2 squared, well, one thing that you have to do, that you can do here is, well, assume the easiest thing to do is to assume that the first step is slow, and if first is slow, okay, then the rate will be equal to K times concentration of NO2 times concentration of NO2, but they are the same, right? So this is equal K NO2 squared, which is pretty much what we have here. All right, so the first step is the slow one. Just by, I mean, you didn't know to begin with, you just assume that it was, you find what the equation is, the rate law is for the first step, it matches, so the conclusion is valid. So step 1 is the slow one, so we can scratch step 2, we can scratch step 2 here. They are not, the step 2 is not the rate determining step. All right, and NO3 is a reaction intermediate versus NO3 as a catalyst. So where does NO3 appear? NO3 is here and here. So NO3 is first produced, then consumed. So it's not going to be there at the end of the reaction when the reaction is over. So it is an intermediate. All right. What is the freezing point of a solution that contains 35.9 grams of glycerin in 322 milliliters of water? Okay, Kf is 186. Well, this is glycerin. Okay, so glycerin is a non-electrolyte. Therefore, I is equal to 1, and delta Tf is equal the molality times Kf. And what is the molality? The molality is moles over kilograms of solvent. All right, so for moles we have 35.9 grams divided by 9209. All right, so 35.9 divided by 9209, this is 0.3898, and the molality will be, since you have 325 milliliters of water and you assume that the density is 1, then this is equal to 0.325 kilograms. Okay, so the molality is 0.3898 divided by 0.325, and this is pretty much 1.2, right? Let's use the decimals. 1.199. Okay, so delta Tf is equal to 1.199 times 186, which is 223, and the freezing point of the solution will be equal to 0 minus 223, which is equal minus 223. Last question. Each plot describes a function of the concentration of a single starting material versus time and what we are looking for. All right, so 0 let me redo this. Okay, this is order linear if it's linear and you are plotting A versus time, that's 0 order. Okay, so here this is concentration versus time, so this is 0 order. If logarithm of A versus time is linear, then it's first order. That's what we have here. Logarithm of A versus time, this is first order. And If linear, when you plot 1 over a versus time, that's second order. And that's exactly what you have here. Okay, so this is second order. Second order reactions are also the only ones that have a positive slope. Okay, so here you have negative slope, and here you have positive slope. That's another way that you can recognize a second order reaction. Okay.